So let's get to our lecture. Good afternoon, and I hope you guys had a good spring break. Also, happy spring, by the way. Spring started about 10 days ago, although we had some snow in Rolla a few days ago. So before the spring break, we kind of concluded, and we are going to actually finish it today, the discussion on current mode control. So the idea behind current mode control is to measure the current of the inductor. All of our converters have at least one inductor, so we measure that current, and I kind of include that in our decision-making process in terms of determining what the right value for the duty cycle should be. Most of the time, the control objective is still the same. You would like to regulate the output voltage against the variations in the input voltage or the variations in the output current or output load or resistance. So we discussed that the most common way of doing current mode control is peak current mode control. In all of these methods, we have to measure the electric current, so that's a challenge by itself. The easiest way of measuring the electric current is putting a very small resistance on the path. But if the resistance is too little, then the noise is becoming a problem. And if the resistance is too large, then there's going to be losses associated with that resistance. Actually, I had a master's student a few years ago who did a survey on different current measurement techniques in power electronics. So if you're interested, her thesis is available in the library. So the first modeling approach, which was the simplified modeling approach, was assuming that the inductor current is exactly following its reference. There is no, for instance, like in peak current mode control, there's a little bit of a difference between the average value of the inductor current and the reference, because the peak is following the reference, not the average value. But anyway, the first the control approximation, the simplified method was assuming that they are identical, then we perturb the system. And we started the discussion for the Buck converter, and then we ended up generalizing it to any kind of converter. So let me see, hold on. So this was our generalized current mode control approach. Then we had an example of using this for instance, boost converter. Also, we had a table kind of summarizing all of these parameters for the Buckboost and Buckboost topologies. After that, we talked a little bit about the more accurate model. We did not go through the details of the more accurate model. I just showed you the results. And basically, if you open up a paper or a textbook and you see a diagram like this, this is referring to the more accurate model. In the more accurate model, the value of the duty cycle is influenced by changes in the input voltage, changes in the output voltage, changes in the inductor current, as well as changes in the reference for the inductor current. Again, we have a table that is determining what these gains of F sub G and F sub V are, which is Fg here, Fv here, and F sub M is, for all these converters, 1 over M sub A times T, and M sub A was the slope of the auxiliary ramp. What I'm going to start with today is I'm going to go through just showing you the differences between the more accurate model, the transfer functions that we will obtain using the more accurate model versus the simpler model. Let me see if I can find it. And this is, by the way, on Blackboard. So I'm using MathGAD, a typical converter that we have, which is again a Buck topology, input voltage of 48 volts, output voltage of 12, inductor is 220 micro, the output cap is 10 micro, the load resistance is 5, and the switching frequency is 75 kilohertz. So I'm kind of following those basically The auxiliary ramp, by the way, I've selected to be half of the negative ramp of the inductor current. I have capped because it's a buck converter. Fm is this, Fg is this, and Fv is this. And overall, if you kind of close that little loop, you end up with this transfer function. And there is obviously phase associated with that. As you can see in the simple model, we were dealing with like a first order model. The inductor was kind of eliminated. The dynamics of the inductor was eliminated. So it was just a capacitor. Here, the more accurate model gives you more information. As you can see, we are still dealing with a second order system. So it's not like we have completely eliminated the dynamics of the inductor. Also, you can actually check it out later. Also, I'm kind of comparing it with two other transfer functions. One of them is the voltage mode control transfer function. These are all GVD or GVC, control to output transfer functions. The blue one is for the voltage mode control. And the green one is the simplified one. And then the red one is the more accurate one. So you can see the simple model and the more accurate model at lower frequencies are almost basically the same. There's not a significant difference between them. The only difference happens above this area, that your simple model in terms of high frequencies does not predict the accurate behavior of the system. And another interesting thing to note is, regardless of what you're doing in terms of are you using voltage mode control or are you doing current mode control, at higher frequencies your control to output transfer functions are almost behaving the same. And by the way, in power electronics, what I mean by high frequencies, like in the vicinity of the switching frequency and beyond, which is not that significantly important because we tend to design the converter so you have a lot of attenuation at the switching frequency. So the important are at lower frequencies, the importance. In terms of phase angle, again, the red one is the blue one is the voltage mode control. Very simple second order system. Phase goes to a negative of 180 degrees. The red one is the more accurate model for current mode control. Again, it goes to negative 180 degrees. And then the green one is the phase for the simplified model, which is the only first order model. Therefore, the phase only goes to negative 90 degrees. Again, you can see that up to this particular frequency, the two models are the same. And that is pretty much where you place your zero crossing frequency anyway. So even though the phases are different at higher frequencies, this may not significantly influence your voltage compensation design. Any questions so far? Yes?
My question is, like, we usually select L and C components.
Right.
Based on the current ripple for L,
right,
voltage ripple for C.
Right.
So suppose on the whole, the corner frequency happens to be actually recommended. The best design for compensator is 1/10 of the switching.
Okay.
And suppose say it's around only 2 times of the switching, like one half or 1/3 of the switching.
Okay.
So how to go about it?
So remember what you said were kind of the same. So you said you designed the inductor and the capacitor based on the ripple. So for instance, you say my output voltage ripple should be less than 1%. That maps into the fact that your corner frequency is much smaller than the switching frequency anyway. Or you have a lot of attenuation at the switching frequency. So if you observe those, design criterion, then you are not going to face a problem that your corner frequency and the switching frequency are very close to each other. Now, if they happen to be close to each other for a very particular design that, for instance, you don't care about the ripple in the output voltage, not a problem. Your corner frequency and switching frequency are the same, are close to each other. You just have to be careful about you're not amplifying the noise in your feedback loop, or in terms of phase and voltage compensation and phase margin, you're in the safe region. But usually that doesn't happen. Usually your corner frequency and your switching frequency are relatively far away from each other, like 5 times or 10 times. All right. So this was all about, this is on Blackboard as well, a little bit of a comparison between more accurate model and a simpler model. Now to prove it to you that the simple model still works, I also have a file that I've tried to design the voltage compensation network using the simplified model to see how it looks like. So we have, again, the same converter, the same input voltage, the same output voltage. Now here I have assumed that Vref is 2.45, and before we get there, let me also remind you, let me see. So the whole discussion is, okay, now we have a, let me see. We have a model for our current mode control, which is from this point all the way to the end, which is the output voltage. What should be the right transfer function for this voltage compensation network, basically? So you're still doing the thing that you're measuring the output voltage, you're comparing it against a reference, you get this error signal over here, then apply to the voltage compensation network. So the question is, what is the right value for the voltage compensation network? So far we have been able to find a transfer function which takes care of this point to this point, which is the control to output transfer function. So that's part of our loop, and the other components in the loop are the sensing network as well as the compensation network, which we are trying to basically find a good transfer function for. So I'm assuming, for a weird reason, my reference, which is provided by the chip, is 2.45 volts, and therefore my sensing network is Vref over Vout. Whatever that number is, it's scaling down the output voltage. And if you remember from our simplified model, our control to output transfer function is a first order model, very, very simple, because the inductor has been eliminated. The dynamics of the inductor has been eliminated. So if you look at the Bode plots of just the control to output voltage transfer function is like this, which we saw also in the previous file as well. Now I am trying to put this transfer function as my voltage transfer as my voltage compensation network. Remember, we still need 1 over S, which is an integration block, to eliminate the steady state error. We have some gain in this particular in this particular case. My gain is 30,000 whatever. And there is a 0 as well as a pole. So the 0 is at low frequency, the pole is at higher frequency. Similar trend, we did it for the compensation network design for a voltage compensation network or voltage mode controller. In that case, we had 2 zeros and 2 poles because we needed a significant amount of phase boost. Over here, in terms of phase, we are doing good. Phase, worst case scenario, goes to negative 90 degrees, so we don't need a lot of phase boost. So I only added 1 low frequency 0 and 1 high frequency pole. So after you do so, again, I didn't come up with a particular design procedure, but it's pretty much the same. You have an integration block, make sure your loop gain is almost a straight line. So remember, our loop gain has these components: voltage sensing network, the compensation network, as well as the control to output transfer function from the converter. So this is my basically loop gain after I add the compensation network to it. Several features that we still have to remember. One is that your gain should be very high or almost infinite at low frequencies, meaning that you want to eliminate the steady state error. The other thing is your switching frequency is somewhere around here. You got to make sure you have enough or significant amount of attenuation at the switching frequency, which we have. Make sure your loop gain doesn't cross the 0 dB or 1 several times. It's better to just cross it once. And most important of all, make sure your converter is stable, meaning that if I look at this crossover frequency over here, which is a slightly less than 100,000 radians per second, I have significant amount of phase margin, which is basically somewhere around here. So I have about more than 45 degrees of phase margin. So stability, high bandwidth, high attenuation at the switching frequency, and also high gain at DC basically. So I have actually simulated this. Oh, by the way, on the right hand side, I am just looking at the compensation network by itself, not the loop gain. So the compensation network has a 0 over here and has a pole over here. They are very close to each other. As you can see, I have placed the pole a little bit higher than the corner frequency, and I have placed the 0 a little bit lower than the corner frequency. And I'm also getting a little bit of a basically phase boost of like 45 degrees or something like that. All right, so you can see that because the simplified model, there's only one pole in it. It's this first order behavior. Designing the compensation network is easier. And then we can look at the simulation results in MATLAB. All right, let's see. Where is it? Here it is. So I have this. I have this converter. We have seen it before. There's a blue box on the left-hand side. Over here, I'm actually manipulating my input voltage. Sometimes it could be constant, or a constant plus some ripple, or a constant plus a step change. Then I have another blue box over here, which is my load. My load is constant, or I can actually introduce a step change in the load or some low frequency variations. And down here is my controller. So I'm measuring the output voltage and then comparing it against 2.45, which is the reference. This is the transfer functions that we just came up with. And so I'm not using an outside or kind of an open loop IRF anymore. The loop is closed. I'm creating an external ramp over here as well. And the rest is the logic behind current mode control that you have seen before. At the beginning of the cycle, you turn the switch on, therefore the inductor current rises. Then whenever the inductor current decides to get larger than the reference, you turn the switch off, basically. Simple. All right, so we are going to look at the behavior of the system. First, like make sure the system is stable, no changes in the system. So things look okay. I would like my output voltage to be 12. It is 12 actually. There's obviously a little bit of a switching ripple on it. We cannot really eliminate that. And the inductor current looks normal. There is no like subharmonic oscillations or anything in it. So everything is normal. Now what I'm going to do is I'm going to slightly kind of compare the performance of a current mode controlled buck converter versus the performance of a voltage mode buck converter. So for instance, let's decide we want to introduce a sudden change in our input voltage. Our input voltage initially it is 45 volts and then jumps to 45 plus 6, which is 51. Like a very extreme case, basically. Well, obviously, we are looking at our output voltage. Ideally, the output voltage shouldn't see these changes. It doesn't matter what the input voltage is. The output voltage should be 12, and as you can see, it is 12. So it's very good. It's doing a very good job actually attenuating or eliminating the changes in the input voltage. Although if you zoom in, you can see a slight difference over here. You can see a very tiny little hump over here. You can see, like, it is almost insignificant compared to the switching ripples. So it's almost insignificant. Also, if you notice, the pattern of the inductor current changes a little bit as well, and that is because input voltage has changed. The slope of the rising and the rising of the inductor current has changed. So there's a slight change in the system, but the system handles it very well. So current mode control did a good job. If you don't remember how voltage mode control operates or behaves, let's look at almost the same topology. However, this time I am doing a voltage mode control. So remember, we were suggesting different voltage compensation networks, and I'm using the fanciest one, the lowest one down here, basically. So let's see how this system behaves if our load is constant, but our input voltage has a sudden change. Let me zoom it out a little bit. All right, now you can see voltage mode control is not doing as good as current mode control does. So you can see we have a larger hump here, basically. All right. Both of them are relatively actually good, but it depends on the load. Maybe the load is even sensitive to half a volt of deviation from its reference, okay? So this is good. Now, so in general, current mode control does really much better compared to voltage mode control when it comes to attenuating the changes in the output voltage, in the input voltage, so that it wouldn't affect the output voltage. Now, this time I'm going to change the load. I'm going to change the load from 4 ohms to 6 ohms, then bring it back to 4 ohms, like a very step change, a very drastic change. And now we're looking at the results of the voltage mode control. All right. So as you can see, well, first of all, the load has changed, the load resistance has changed, but the output voltage is supposed to be the same. So you can see that the output, the inductor current changes. Ideally, it should step up and down, basically. If you look at this over here, we have seen it before. You can see that the system has like an overshoot and then an undershoot, and takes a little while for the system to kind of recover. It takes about 0.5 milliseconds, a little bit even longer than that, for the system to recover. And the overshoot that we have goes as high as almost close to 14 or 13.75 volts. So this is voltage mode control. Now let's compare it against current mode control. All right, so I'm going to keep the input voltage constant and change the load. All right, you can see that still we have the overshoot and undershoot over here, but let me zoom in and see if you can compare them. So the overshoot in terms of the peak value, it's almost the same. It gets close to 14, like 13.75, so we didn't really improve that. But in terms of recovery time, it's a little bit doing better. The previous one took like 0.5 milliseconds to recover. This is taking maybe 0.4, a little bit better than that. So current mode control does not significantly improve the dynamic performance of the system when it comes to variations in the output power or output resistance, basically. And there is a reason for that. You can actually explain it. When you have a sudden change in your converter, let's say we have a buck converter. So let's say your load resistance suddenly changes from, I don't know, 5 ohms to, for instance, 8 ohms. Okay? That means if you want to keep the output current, the output voltage constant, that means the inductor current should also experience a change like this. So before, load was a small, current was larger. Now the output load is larger, therefore the current should be smaller. So ideally, this is your inductor current, but practically, your inductor current has some ripple on it. All right, something like this. So let's say as soon as the load changes, you realize the load has changed and just keep the switch off, meaning that don't send energy to the output, let the output capacitor to discharge by itself. But even though you are keeping the switch off, still your inductor current is not following its reference in this area. All right. So the switch is off. The best that you can do to reduce the value of the inductor current as much or as quickly as you can. But the reference, or ideally, you want it to be like a step change, but practically inductor current follows a slope, which is V out over L, basically. So this difference between these two areas, the capacitor actually sees the difference between these two, and it is integrating the difference between these two. So you always have a dip or overshoot in your output voltage, okay? So that is very natural. Do not try to eliminate it. But then the system recovers a little bit quicker this time, okay? Although there are techniques that you can even make this a little bit better, one technique is instead of doing current mode control for the inductor current, do current mode control for the capacitor current. So for current mode control for the inductor current, we say, we have a reference for the inductor current, and the inductor current should follow it, and that represents regulation in the output voltage. If you do it for the capacitor current, you always want the capacitor current to be 0 on average, basically. So your capacitor current is always following almost 0, basically. So you have a voltage compensation network. The output of that voltage compensation network is always almost 0, and the capacitor current should follow that. That system behaves a little bit faster. There are other techniques, and that is, for instance, somehow manipulate the value of the inductor, and if you observe a transition or something like this, remember this slope is V out over L. Okay? So if you somehow during the transition I manipulate the value of the inductor and make it smaller, this slope is more steep. Therefore, you will have something like this, for instance. Now, let me just check. Hold on. I didn't draw it really. Okay, so let's say you have manipulated the value of the inductor so it's smaller, then you can get it larger again. All right, so now you can see the difference between the actual value of the inductor current and the ideal value of the inductor current is smaller, therefore that overshoot is going to be smaller. Yes?
How do you manipulate the value of the inductor?
Excellent question. Practically, it's very difficult. In like low power applications, you can. With some, like for instance, your winding could have a core that moves a little bit, for instance, so you can make it smaller or larger. You can have some sort of a mutual inductance and manipulate with that mutual thing, something like that. Like at chip level, it's possible. At larger levels, it's very complicated. The other thing that you can do, and I had a PhD student actually working on this, was he was adding an H bridge over here. Okay, this is an H bridge. And what did H-bridge did was, if it observed a transition, it applied a very large in terms of positive or very small in terms of negative voltage across the inductor. So he was trying to manipulate this number over here, this V out over here. And he was getting very, very, very quick responses. So if you're interested, let me know. I can actually share his papers with you. So it's an interesting topic to work with. There's a lot of researchers working on improving or optimizing the performance of the current mode control, but those are kind of beyond the scope of this class. I just wanted to introduce them to you so you know that some other approaches or fancier approaches exist. Now what I'm going to do is I'm going to have a little bit of a quantitative comparison between some of the transfer functions that we have for the voltage mode control and current mode control schemes. So let's say voltage mode control versus current mode control. All right. So one of them is control to output transfer function. If you remember, for the voltage mode control, we had like a quadratic behavior, and we had like a behavior like this when it comes to control to output transfer function. Our control is the duty cycle. But for current mode control, we have something like this. All right. Here I'm using the letter C because D is not the control parameter anymore. It's actually IRF, or just a control signal, something like this. So they are a little bit different. At high frequencies, they kind of become similar. Also, if you look at their phase values, let's say this is 0 degrees and this is negative 180 degrees. This is the phase angle for GVD, and for GVC, the control, the current mode control approach, it's a little bit smoother, something like this. And by the way, these are coming from more accurate models, okay? Because in the simple model, GVC, in terms of phase, it only goes to negative 90 degrees. Okay? So that's one difference. The other one is audio susceptibility, okay, input to output transfer functions. Let me draw it actually here. Well, we would like this transfer function to be as negative as possible, or almost 0. But this is for voltage mode control. So it's actually not very small, and then our feedback loop should take care of that. And then for current mode control, the simple model predicts that it should be negative infinity, but using the more accurate model, we end up with something like this. Okay? And this is negative 40 dBs. So it's actually very small, which is actually quite good. We don't care about the phase of this thing because it's not part of our closed loop system, and not part of our, we don't look at it to determine the phase margin. The other feature, or comparison between these two, it comes when you are looking at the output impedance, basically. So let me draw it maybe down here. Remember, ideally, we would like our converter, like when you have a source, you always want that source to have a kind of a negative, or very small, or in terms of dBs, negative output impedance. And actually, voltage mode control almost does that. So if you look at voltage mode control, you're looking at an inductor placed in series with in parallel with a capacitor, and then in parallel with a resistor. So at very low frequencies, it is actually the internal resistance of the inductor that is determining the output impedance, and it's very small. Then we have like an LC tank, so it actually, inductor kicks in, then capacitor kicks in, and it becomes something like this. Okay? So actually, voltage mode control does a good job in terms of having a low output impedance at lower frequencies. But unfortunately, current mode control does not. It looks more like this. All right. So this is current mode control. And the reason is, for the current mode control, remember the inductor or the dynamic of the inductor is eliminated. So at low frequencies, what we have left, at low frequencies, capacitors are like open circuit. So at low frequencies, what we have is just a resistor, which is our output load. An output load is not necessarily small, therefore we have a large output, actually, impedance. Then at high frequencies, the capacitor is the smallest one, the most dominating term, and it becomes close to what we have for the voltage mode control anyway. So this is a bad thing for current mode control, that the output impedance, at least for the buck converter, is larger than when we control it under current mode control. All right. Any questions? Yes.
Low frequencies for a current mode control, so we would have 1 over SC.
Okay.
So 1 over SC is basically infinity.
Yes, but that infinity is in parallel. So we have a large impedance, which is the impedance of the capacitor, in parallel with the resistor. And resistor is a dominating one, so only resistor shows itself.
Yeah. Okay.
So remember, DC current doesn't flow through the cap, so it goes through the resistor. Any other questions?
I have
Yes.
some questions.
Go ahead.
So, relating to the question which came up in the quiz, if we were to
No, remember, we are not going to talk about the quiz
that's
because
fine.
we have a
That's
student.
fine. So
Go ahead.
if at all, so we had a V out and we had a duty ratio and we had something for the first part, and then we had a V out and then again a duty ratio for the.
Okay.
So if now, so I know that I have a specific output voltage to be met.
Okay.
So would I just have to tune the controller every time if?
Oh, you mean if you want to regulate the output voltage,
Yeah.
right?
Now I have a different requirement for an output voltage.
So is your output voltage supposed to be constant?
No, I mean it was 19.2 and then it was 14.4.
Okay.
So-
All right. So if you have it, okay. So if you have it, let's say you have an application, and actually we have real applications like this. So let me tell you the application. It's called dynamic voltage programming or something like this, and that is to optimize the efficiency of a central processing unit in a computer, in a motherboard. So when the motherboard is consuming a lot of power, let's say you are running some simulations and you're using a lot of computation, therefore your central processing unit is consuming a lot of power, and you, for instance, is consuming 50 amperes of current. All right. Now your output voltage should be very small. If your current is too high, your output voltage should be very small, because somehow current times voltage represents the power delivered to the CPU and the losses that happen in the CPU. Okay. And unfortunately, in those regions, your converter is not very efficient, but the CPU is the priority for you, so you feed it with a very low voltage and a very high current. Then when you are in a standby situation, your CPU is not processing much power, and then your current maybe is only 2 amps. Now, your converter is your priority because you want to operate your converter at higher voltages because it's more efficient. So instead of providing like 1 or 2 volts to the output as for your CPU, you give it 4 volts this time, because CPU can handle those losses even though your voltage is larger. So there are applications that you want to have a good control on the value of your output voltage. Now, if such a thing happens, if you have such an application, so technically all you have to do is go to this diagram. Okay, what happened? Okay. And change this VREF. Okay? So you can dynamically program the value of, like in the example that I said, VREF is dynamically programmed based on the processing power or computation of the CPU, basically. Is that your question?
Yeah, my question was just that, I mean, if in case there is a requirement that now you need a different output voltage, so does an engineer require to manually change the settings of a compensator or a VREF every time?
Okay, excellent question. Yes and no. I would say no, because manually you should design it once and it should work forever. The designer should be aware of this requirement and design the system based on the worst case scenario kind of a thing. Okay. So for instance, when I was designing this MATLAB file, let's take a look at this. When I was designing this, my assumption was the output voltage is always 12. Okay. Now let's change it a little bit. See what happens. Oops. Did I delete anything? Oh, hold on. Deleted the wrong. Okay. Now let's say I have an output voltage that initially is 12. 2.5 represents 12. And then it has to jump to twice that. Twice 2.45. Very extreme, actually. So let's see if my system can handle that, okay? Or is it going to go unstable? All right. Now, let's make everything else constant. Like my load is constant 5 and my input is constant 48. All right. It did it actually. So I didn't even have this in mind when I was designing the compensation network. You can see my output is 12 before, then it jumps to 24. There's a little bit of an overshoot here as well. So because it's behaving more like a first order system, it's not very critical, but yes, the designer should have that in mind when you're designing the system for the worst case scenario. Now, what is worst case scenario? I'm afraid to tell you something, then you find another worst case scenario. So worst case scenario is either your input voltage is too small or too large, or somewhere in between, something peaks or something like that. Or, okay, so let's do it this way. Looking at the MathCAD file, let me see, where's the MathCAD file here? So I have designed this, and now I want to do like it's called sensitivity analysis, basically. So now let's say if my V out is supposed to be twice as much, right? Twice times 12. Do I have any stability problems? Let's go take a look. See, my loop gain is still normal. In terms of phase margin, this is my crossover frequency. So my crossover frequency have moved to the left a little bit, actually. And I'm expecting that, yeah, my system is actually more stable than it was before. So the worst scenario in this case was when your output voltage was 12, not 24. Okay? All right, very good question. Other questions not related to the quiz? Okay. Okay, so this was all about current mode control. Interesting topic. Has been invented since the 70s, probably before you guys were born. And there is still a lot of exciting research going on. I mean, improving it, making it faster, things like that. Now, I want to introduce another topic, and that is having an input filter for our converter. Since we are doing a lot of these small signal models and a lot of these transfer functions, let's talk a little bit about that. So let's talk about input filter. If we just limit ourselves to the classic Buckboost and Buckboost topologies, and Buck is everyone's most favorite because it's the simplest one. I'm intentionally drawing it a little bit long. Okay. So let's say we are operating under continuous conduction mode. The inductor current looks good, but if you look at the input current, it doesn't look good. Right? The switch current or the input current is actually discontinuous. So this is one of the major disadvantages of the Buck topology, and that is the input current is discontinuous. So you may say, oh, no problem. All I have to do is just place a filter between the source and the converter. So first of all, why is this a bad thing to have a discontinuous current? The bad thing is if you have some internal resistance in your source, then if you measure this voltage, your voltage is not the DC and constant DC anymore. You're going to see some fluctuations in the voltage as well. And if there are other loads connected to this source as well, they are going to see those fluctuations as well. So you have all of a sudden you're actually propagating a lot of noise into the system. So you may say, no problem. All we got to do is place a filter between the source and the load. For instance, the simplest filter would be just a capacitor. Okay, so you put the capacitor as close as possible to your source. And sometimes putting the capacitor is actually quite normal. You are not going to face any problems in terms of stability. And this happens a lot when you're dealing with solar panels, okay? So the current that you're drawing from a panel, because at one particular point you have your maximum operating point, the best operating point, should be almost a DC current. But the converter doesn't draw a DC current. If it is a boost converter, it's better than buck, but sometimes you may have a Buckboost or something like that. So that's why they put an electrolytic cap between the solar panel and the converter. But sometimes you may say a first order system, which is this cap, is not enough for me. I want to actually make the current even smoother and place an inductor here as well. So it's like a second order filter, okay? So in that case, your input current, again, depends on the size of the components that you're using. It is almost a DC current. And therefore that problem that we have goes away. So if you have other elements connected to the source, they are almost seeing a DC basically current or DC voltage. All right. So, yes?
Will that not cause problem in the control part? Like the order of the system increases?
That's absolutely correct. And that's what we're going to talk about. So as soon as you mess with your source or your load, you're going to realize later that all of your transfer functions are going to change. And sometimes your system may go unstable because of those changes. Excellent point. And yeah, exactly. So that's what we're going to talk about. So this is the problem they were facing back in the 70s. As soon as they added the filter to the Buck topology, it went crazy basically. So, and they couldn't actually explain it until they came up with these small signal models and stability and control, analysis. So let's see this in simulation. Actually, it happens in simulation as well. Again, this file is already uploaded on Blackboard. All right. So here what I have is in the bottom, I have my classic DC to DC, in this case, the Buck topology, and it is controlled by a voltage mode controller. So I have this voltage mode control block over here. This is my the selected transfer function or compensation network. On the input side, I have added an LC filter, and it doesn't look like an LC filter, but the math is following the math of an LC filter. Obviously, if you're doing Plex, it would look like an LC filter. And to make a comparison, let me now zoom in again. So I can choose from two different sources as my input voltage. When one of them is when my input voltage is just the for instance constant DC source, and I have to switch V source. So that means there's a short connection from here to here. Or I'm selecting Vn, which is the output of my filter. So if I want to put the filter in and out of my converter, I just have to manually go up and down. All right. So I have placed a filter. This filter has one inductor and one capacitor, and I will explain what this RF is later. But for now, let's say it doesn't exist. It's 0. And I am using the filter. So this is in the down position, and my input voltage is also constant. All right. All right. You can see that the system is going all over the place. I just added the filter to the classic voltage mode controlled buck converter, and it basically went crazy. And if you don't believe me, just bypass the filter and look at it now, and it looks normal. So you just add the filter, it goes crazy, take the filter out, it goes normal. So the solution is, to the filter that I have added, and we're going to explain this solution, but I just want to give you the solution first. You got to add a little bit of a resistance here. Okay? Like half an ohm of resistance. And that makes the whole difference in the world. And here's the proof. Okay, so I'm going to add this resistance here. And you can see it goes normal again. So why is that? Why is that we add a little bit of resistance there? It makes a big difference. That's what we are going to actually study. And I want to actually extend this to beyond just adding a filter. So technically, whenever your converter sees some sort of an impedance, what is the features of that impedance so that it would not interfere with the operation of your converter? Now, this impedance could be a filter, it could be the internal impedance of your source, or it could be another converter. It could be another DC-DC converters upstream, so you're looking at the output impedance of that upstream converter, basically. All right, so let's discuss this. There's a little bit of a math involved. I'm going to try and make it as straightforward and as simple as possible. So since we are talking about the buck converter, so let's look at the small signal model of a normal, without a filter, buck converter. So these are the perturbations. This is the perturbations, small signal perturbations of the input voltage. If you remember, the small signal model was like this. Okay. Okay, something like this. And later on, the math is going to get a lot more complicated, so I'm just going to label these impedances in this way. I'm going to label this impedance as Z2. And this as Z1, basically. So I have like an impedance divider on the right-hand side of the system. Okay, so in order to look at the stability of the system before and after we add a filter to it, we got to look at GVD, basically, control to output transfer function, because ultimately this is the transfer function that appears in our loop gain, basically. So remember, this is how it was defined. All right, so remember from our notes, since the input voltage is not being perturbed, on the left-hand side I have like a short circuit. All that is happening is these perturbations over here are going to be reflected to the output side using this impedance divider. That's it. And if you remember, it looked like this. Okay? And we had that, quadratic form and everything like that. Okay. So this is when we do not have a filter. Now I'm going to add the filter and look at this transfer function again. So we already have one inductor in the system. I labeled this to be L of F, the filter inductor, and then C of F. And the rest is the same. All right. Okay, something like this. Okay. So I'm going to, as it was mentioned earlier, because we have added one inductor and one capacitor, extra inductor and extra capacitor to the system, we're now looking at the fourth order kind of a transfer function. So it's going to simplify it a little bit. And remember, I'm only looking for GVD. And since for GVD the perturbations in the input voltage is 0, I just short it. So technically I short this, and then if I short this, I will have the LF in parallel with CF on the input side. And I also label this to be ZF. So we have three impedances labeled: Z1, which is the impedance of the load resistance and the output capacitor in parallel; Z2, which was the impedance of the inductor; and then ZF, which is the impedance of the input filter placed in parallel with the input inductor placed in parallel with the input capacitor. All right. So now I'm going to draw the equivalent circuit model. Okay, I think we're running out of time. I'm going to explain it to you next time on Thursday, the remaining of the math, and how is it that if we add that little resistor to our capacitor, the oscillations are going to go away. So see you guys on Thursday.